inclined plane and a pulley. Let's put together two concepts that we've worked on before. The inclined plane, this guy right here, and the pulley. Find the acceleration of the two masses on the incline. Okay, this mass here is on the incline. This mass is connected to the other end of the string, and it's pulling down this way. And this box is going to go like that. You have kinetic friction between the box and the incline. Assume the two masses are connected by a string of negligible mass that does not stretch or compress, and assume a frictionless and massless pulley so that rotational effects need not be considered in this problem. Start by drawing all the forces you can think of on the two boxes and show the acceleration vectors for each box. What if you choose the wrong direction for the acceleration? Here's the forces, and should you choose a different direction for the acceleration, for example, if you chose this box going this way, you'll get a solution at the end that shows you have a negative acceleration, which means it's not going this way at all, it's going this way, so don't worry about it. So let's look at the forces. Over here on mass 1, we have gravity pulling it down, and we have the force of tension pulling it up, and we're saying it's going to accelerate in the down direction. One thing you do have to do when you choose the acceleration vectors is they have to be consistent with each other. So if you say this box is going down, you have to say this box is going up to make sure the math works. Now, we equally could have said this way for the box on the incline, and this way for the box hanging off the pulley, in which case our answer would be negative. So let's just get rid of all these arrows so we can look at the free body diagram on the box on the incline. And what do we have? We have the normal force, which is perpendicular to the inclined surface. We have gravity, and make sure you call that M2. This is M1, this is M2, because later on you'll be in a position, if you have the M's, you might decide to cancel them out. You can't, they're two different masses. You also have kinetic friction, which is opposing motion, and you have your tension force here. We now remove the sketch and we're just left behind with the free body diagrams. So we're going to call this one with mass 1, system 1, and this will be system 2. And please note we have a rotated coordinate system here, and we've already expressed our gravity in its x and y coordinates with the new rotated coordinate system. We're going to go over these in great detail in the next few slides. We're going to solve this each system separately and then combine them. After we do this, we'll choose different systems, okay? And I'll just give you a hint. One system will be both of the masses together, but we're going to wait for that after we go through this first way. System 1 is the M1 block. We're assuming that the block is falling, hence the direction of acceleration is down. Once we solve the Newton's second law equations, if we get a negative value for A, that just means it's accelerating in this direction. This one's pretty straightforward. Gravity pulling down on the mass, and the tension in the string is pulling it up. This system is a little more complex. We have our rotated coordinate system, so it lines up along the acceleration vector, and so we only have to resolve gravity into its component parts. Note that the normal, tension, and kinetic friction are all aligned with this rotated coordinate system. We're choosing acceleration in the up direction, and again, and hopefully this will be the last time I say it, it's not important which direction is chosen. However, you have to choose the directions for both boxes that are consistent, because we're going to have the same acceleration when we solve the problem, so they sure as heck better be in the same direction. And I'll try not to say that again, I just want to make a point. So let's see what I'm saying there. If block M1, that's the block hanging off the pulley. Right, this is block M2. This is block M1. Right? If M1's going downwards, then M2 has to be accelerating up the incline so we're consistent. The friction force is shown opposite the direction of the acceleration, the proposed movement, of the relative motion of the box and the plane. The tension force is acting upwards. Now here's a key point here, and this will not be true when we get into rotational motion. We have pulleys that have mass on them. Since the string is massless and it doesn't stretch, and the pulley is massless, the two tension forces are equal. And again, when we get to rotational motion, this will not be the case. We'll have a different tension on either side of the pulley. So our preliminaries are now out of the way. Time for Newton's second law. So first try and write the equations, and hopefully this will be fairly straightforward, for system 1. The sum of the forces in the y direction, right, up and down, is going to be negative tension. And why is that a negative? Acceleration is pointing down, tension is opposite the acceleration, it gets a negative sign. m1g is positive, and that equals m1ay. Ensure you keep the subscript for mass 1 to distinguish it from the other mass. And we have negative tension plus m1g equals m1ay. Okay, it's just the acceleration of block m1. Now the only thing to watch out for here is that this is a non-rotated coordinate system, so y is in the up and down direction. However, when we do the incline, right, here's our incline which we're going to get to, this direction is the x direction. So what are we going to say? Well, we have ay due to this guy, due to block 1, that's going to equal a sub x for this guy moving up the incline on its rotated x direction. For system 2, we typically start with the y direction because that will have us find the normal force, which we will need to calculate the friction force here in the x direction. So in the y direction we have the normal, and we have negative m2g cosine theta. That's the component of gravity in that y coordinate system. And that's going to be m2ay, and that will be equal to 0 because it's not bouncing up and down. So the normal force is m2g cosine theta. Friction now is mu k, kinetic friction coefficient, times the normal. So that will be mu k m2g cosine theta. Let's go to the x-axis. And let me just erase this so I can highlight the x direction forces. Well, we have tension in the direction of the acceleration, so that's positive. We have kinetic friction opposite acceleration, negative. And we have the gravitational force in the x direction opposing the motion, so that also opposing the acceleration, that also gets a negative. And that's equal to m2ax. Now we sub in our friction calculation for this guy right here. We get tension minus mu k m2g cosine theta minus m2g sine theta is m2ax. And then we just factor out the m2g just to make this look a little nicer. We now have two simultaneous equations for tension and acceleration. What are they? Well, here's a hint. This is one of them. So let's go to the next slide. We have our free body diagrams up here. And here's the equation from the previous slide. That's for this box. And this is what we calculated first, the free body Newton's second law for system 1. We have two equations. We've done something here with the acceleration. Okay, we took away the subscript. Why? Well, because the acceleration of both boxes is the same. They're connected to each other. They're going over a pulley whose only function is to redirect the motion. It takes no energy to spin the pulley. We're assuming it is massless, so we're ignoring the rotational motion effects. So what we do, we said ax was equal to ay equals a. So we've gotten rid of a variable. Now we just have one acceleration. What's next? We have a system of equations. Both must be true because they're describing the same physical condition. So let's add them together. And note that the tension force cancels out, which is good. And that will actually, that's kind of a foreshadowing for when we solve this the second way, where we assume the whole collection of the two boxes and the pulley and the plane all act as one system. But we'll get to there. So what do we have? We have this equation here, m1g minus parentheses mu k cosine theta plus sine theta times m2g. And note, that's why it's very important to keep track of your subscripts so you don't cancel any of these people out, equals m1 plus m2 times a. Do a little algebraic manipulation, rearrangement, and that's the value for our acceleration.